Hi, my name is Terrence. I'm a senior at SJSU studying biomedical engineering, and my project is on the orthopedic applications of additively manufactured porous 316L stainless steel sample. Now, our motivation behind that is that the one thing with traditional implants is one thing why stainless steel isn't used more for orthopedic implants is, for one reason, it's the issue with stress shielding comes up a lot. And what that is that because stainless steel is such a stiff material, one thing that happens is when you put it in contact with the bone is that it'll take on more of the load that the body puts on it as opposed to the bone, and over time what that can do is that it can cause bone reabsorption, which can affect the implant, the fixation of the implant over time. Now, one way you can solve that is inducing pores throughout the structure, which can reduce the overall stiffness and make it a better match to the stiffness of the bone, which would lower the possibility of stress shielding. Now, there are traditional methods of inducing pores within materials, but one issue with those traditional methods is that they produce a gradient of different sizes in the pores. Now, with additive manufacturing, it could, in theory, produce a consistent pore size throughout the sample, which is one thing we decided to focus on. The pore sizes in general is important because not only does inducing controlling the pore size will affect the overall stiffness, but there's also an aspect of fixation, the bone ingrowth, which helps with the fixation. Now, if you were to look in literature, the optimal pore size for bone ingrowth it's generally controversial, but we just chose a range. We just chose the pore sizes of 100, 200, 300, and 400 microns for our project, and that's just solely so we have a base to work on. So, from the results of our project, you can see that right here. Our project focused on inducing pores through varying the crosshatch spacing, and our results show that you could.
We'll be over here.
Are we okay?
Keep going.
One thing.
Point to your poster and point it out.
One thing that you can see is as you could that pores are that using the metal 3D printer here at JWO, that pores can be reliably induced throughout the samples, but the one issue that we had with these samples is that as you might not be able to see here, but as you increase the crosshatch spacing for the samples, it started losing integrity in a sense. Of the structure started losing integrity, and you can see here by the inconsistent melting, and basically it caused there was a lot of metal powder that wasn't melted completely, which affected the overall surface structure of the sample. Now, in terms of the actual results, we were able to confirm that the porosity does decrease or increase in a consistent manner as you increase the pore size, which seems to indicate that we could control for a certain pore size within the sample. Now, one thing in the future that we hope to be able to do is to verify the porosity throughout the sample in thicker samples, because one thing that we couldn't do here was that because 316L is such a thick material, we could use the technology like CT and X-ray to get a better sense of like what the porosity might be like in the center of a thicker sample, which is important because for implant fixation, the interconnectedness of the port is an important factor for the fixation to be reliable. Also, for future work, we hope to be able to conduct some biocompatibility testing on the samples to see how they might interact with the osteoblasts or the bone cells. Unfortunately, we couldn't finish those tests like within the given time frame. So hopefully we'd be able to finish that in the future. Now, in conclusion, we could. There was for future work, we also hope to be able to maybe see how to see how like the metal samples, how the osteoblasts attach to the samples. That's something else we hope to be able to do. For our project, I'd like to thank our SJSU advisor, Dr. Guna, our Jabil advisor, and Babasa, and thank you to the Jabil team for offering their support to us.